Hello, everyone. Today I will be presenting this paper called Mercury, Efficient On-Device Distributed DNN Training via Stochastic Importance Sampling. And this is the outline of my presentation. First, we'll talk about the motivation. So deep learning model training has been applied to many applications, as you might see, smartphones, and AR, VR headsets, smart speakers, robotics, and drones. All these, a lot of the applications needs to do a lot of training with deep learning. So in the past years, we have this contribution, which is the distributed training. And what there are some limitations to distributed training is that because nowadays a lot of applications are done on device, so it requires a significant amount of training time, especially for a lot of devices we use nowadays. And also limited bandwidth slows down the communication process. So here is a very simple formula. It's just saying the total time is E stands for the epochs, which is the iterations of training, and TCP is the time for computation, and TCM is the time for communication. So these factors affect the total training process. So if we have slow communication and we have high amount of training time, it will slow down the training process. And this is give an example of how distributed training is used with Wi-Fi, which is another big challenge when it comes to limited bandwidth. So what we've been doing before is we had come up with some solutions. So first one is the gradient compression. So basically, there are two ways to see this. First is quantizing the gradients. So you represent those gradients with smaller number of bits to reduce the size of it. And or you can use sparsification, which is we select the important gradients to do the training. And those two methods are altogether called the gradient compression. What it has its fallbacks is that it sacrifices the accuracy of the trained model. And the next thing is the local SGD. So what it does is clients, they can perform multiple local updates before doing the transmission to the server. And what happens here is that they might deviate from the global optimal model, because every local model we train separately. If you want to reduce the communication, you must have more steps to do so, as this graph indicates. So in that case, if we try to do more local steps before transmitting, we might actually affect the accuracy of it. And the third solution is overlapping. What it means is to overlap the communication with the gradient computation, which means you can do the computation and communication in the same time. So what it does is mask out the communication costs, since when you're doing together, the time that needs to wait for the communication can be masked out. And what is the problem is because right now on-device communication is way higher than the gradient computation. So here's a figure to show what that means. So if we have a environment with high bandwidth, as in the left, as you can see, the doing the overlap will really effectively reduce the amount of time to do the training. But if we are in a low bandwidth environment, that means the communication time is way higher. So even if you do the overlap, the overall performance is limited, which is why this is the limitation of overlapping. So what does this paper tries to do? What it really tries to do is to improve the training efficiency. And by doing so, you can reduce the iterations for convergence, because for each iteration, you have a more efficient training. So you only need less iterations to do so, to reach the performance you want. And the key concept here behind this Mercury is the importance sampling. So data importance distribution differs as the iteration goes up. As you can see in the upper left of this figure, is when the iteration is 0, the data importance is distributed in this way. And as it goes on to 200, to 400, and eventually to 1,000, you can see there are more and more data that are being viewed as not really that important, as into train the model. So as iteration goes up, you can see more non-important data are appearing. If we try to do this in a random sampling way, this is all the training data in there. So if we do the random sampling, we just get this 6. We set the mini batch to 6. So this is the 6th sample we want to get. But if we do this in a importance sampling way, that means more important data, more data that are affect more to the training will be sampled this way. So as you might know, as the colors turn dark, that means more important the data is. So in importance sampling, in this example, they have 3 black dots and 2 close to black dots and a gray one. But in the random sampling, you just can't get this out of luck. So this is a basic framework of what Mercury tries to do, is to replace the random sampling to a importance computation sampling. That way, if you use those that are more efficient to the training, you can eventually reduce the iterations of it. And of course, this entire process is not that simple. There are many challenges to such approach. So the first one is it still costs you to do the importance sampling. Since to do the importance sampling, you must first know the importance of the data. So you have to perform a importance computation first. So here is a full demonstration of the speed up. So E represents the iteration of standard SGD, and EIS is the iteration of importance sampling. So ideally, this EIS is lower than the E, because you get more efficient training. But you can see in here, TIS is the importance computation time. So if this importance computation time, sampling and computation time is too high, that it will overshadow the benefit of you reducing the iteration needed to do so. So we must make sure that this computation and sampling cost is low enough. And what is the first solution to this challenge is we use the group-wise importance sampling. What we do is we divide the training data into groups. We only update the importance distribution for one group at a time. So that way, we don't need to compute all all the data to look for its importance. And we can reuse the cache distribution from other groups. Here's a figure to demonstrate what that means. So in the left, we try to get 4, the mini batch is 4. So we try to get 4 out of these 4 groups. But instead of just, we have to compute all those 4 groups and then extract 4 data from it, we can actually choose to select some of them and to use the data from there. So this way, we don't need to compute the entire group. We only need to update it one at a time. So every time we do the process, we update one group, and we can use the information we already know from the previously updated example.
I have 2 quick questions here.
Okay.
So first of all, the grouping itself, right, is going to take some energy and take a certain kind of cost, time, energy, whatever. Do they consider that? The cost of grouping.
Okay.
Did they consider that?
They do, but they in the result, and they just pretty much neglect the effect for the group. So what they think is that the computation is much faster. So even if you need some
No, first of all, you need to consider the cost of grouping. It doesn't matter the time or energy, right? The second thing, you said that you're going to reuse the cache distribution from other groups. Well, if you cache something, you need to store them into the memory, right?
Yes.
As we know, if this information is large, that's going to cost some energy as well. Time, probably no, but energy too. Energy, they consume some energy too.
Yes.
Did they consider that?
They did not really mention about this.
Okay, so what's their metric finally? Is it time or energy? Overall time or overall energy?
There is the time to be there.
Okay, if the time, it makes sense. Okay, you don't consider this the actual energy consumption, but that's actual. I don't know. Probably it's not. It's not a lot, but still, it's actual cost.
Yes.
But you need to, at least you need to consider, the grouping time, right? Also, yes. Could you go to prairie size?
Okay.
This one, you're talking about, okay, if I do important sampling, how much speed up, I can create or something, how much speed up I can do, right?
Yes.
But I think you cannot do this. What you should compare is, I just do random sample, compare with important sampling. Which one, speed up more? This speed up is not because of you do important sampling or whatever. It's because you do sampling. You know what I mean?
Yes, I understand.
Yeah. Also, I don't know if you do the important sampling, are they going to cause any bias for final training? You do random sampling, there is no bias, right? But if you do important sampling, there definitely is going to be some bias for the final, for learning results. Have they talked about anything, discussed anything like this?
They do have a mention about the bias thing, and what they do is they perform the resharding to avoid that kind of a situation.
Well, now I get confused. Why I need to do the important sampling? I add extra time. Why just go ahead the random sampling? I think that's good enough. The important sampling help you to faster convergence or achieve
Yeah,
faster convergence or something?
yes, because like in this one, as you can see, if you do the importance sampling, you can get more data that will help you accelerate the thing, because
Then
these are more important.
how do you define the importance of the data? Define.
So,
Yeah.
so that is different from every case, but it's like if you have for example, if you want to do a image classification and you have some features, so there are some data that will make much sense. So if we want to classify a car, then the the thing of having a wheel is more important than the colors blue, because blue can be anything. It could be the sky, it could be the ocean, and it could be anything. But in this case, there are some variants that affect more or to the goal you wanted to reach. Like for a car, you need knowing that it has wheels in the photo, in the picture, is more important than okay, you see something blue in the picture. So in that case, they can that's how they determine like what data might be important.
Does the importance sampling can understand, for example, the car or the wheels in the image? And how?
Yes, I think
yes.
Dr. Wang's question makes sense.
Okay.
From a human eyes, definitely, yeah, you can say that the car wheel is more important than the rest of it. But for a computer, how can you make them to recognize those? How can you distinguish the important data from the other data?
If they can recognize the wheels, then probably the job is done, right?
Yeah.
It's the checking and the
why do you
egg.
need the classification learning? Yeah.
So from my understanding, I mean, the importance could be interpreted in this way. So we read the paper OORT, the OORT, right? So in the paper OORT, they will have two metrics. One is for two metrics for each client. So one of the metric is the statistical efficiency. Okay, then how do they calculate the statistical efficiency? They calculated by measure the contribution to the gradients from each data sample. Okay, so we can measure how much updates a data sample can contribute to the gradient update. The larger the gradient update is, then we can say this data sample is more important because it brings more like updates. Can we understand it in this way? I mean, for this importance sampling.
Yes,
I think Dr. Wang, what you mentioned is, you measure that during the training. For this one, it seems that it's not
Right.
like you measure that during the training. It's like
before.
Yeah. This is
So
kind of
basically
pre-processing, right?
Right,
Yeah.
right. Data pre-processing. Yes, right.
I got confused. How can you justify you at least you need to, this is a SenSys paper, right? At least you provide how do you do the experiments, right? So if you don't theoretically, illustrate, how can you define the importance? At least empirically.
I think importance sampling
should
be an algorithm, an existing algorithm. The importance should not be like a general importance. It should be something like a terminology for the sampling techniques.
Okay.
It's not like how important or not important. I mean, the importance sampling should be an algorithm. If we do the Google, I think it's an algorithm based on statisticals. For example, okay, if some of the data are close to each other, right, then the data in the center of those like subgroup of data could be more important. than others. I think the importance sampling should be about this. It's not general importance.
Jiahao, you provide a paper, right?
Yeah.
Right.
So Dr. Wang mentioned is correct. Since like the importance means like the each data, they in the because like for general SGD, right, we just randomly choose the data and the training. But for importance sampling, they choose the important data instead of random sampling. Why the importance here? Because when we introduce general SGD, we have a sample variance. After we consider important sampling, we should make each sample have a weight. We try to minimize the weight or choose the weight before we before we do the sampling, and try to minimize the overall variance. And they have a optimization problem, like minimize something objective and have a constraint, try to get a distribution. This is very like a communication costly. Communication costly.
But the thing is, the paper you provide is still you do the sampling during the training.
Yeah, we should change the sample each time. That's the reason you can when I go to the previous page.
Okay.
That's you show this paper, right? That at the beginning all the distribution look like this one, and during this training the distribution, the important distribution change, right?
Oh, okay. Data importance 50%, major of them. Okay, little by little with the iteration, important data becomes less and less, right?
Yeah.
Important data samples. Oh, so basically they try to sample the important data according to what Dr. Wang described and what is the paper you provide, right?
Yeah, that's called the important sampling SGD. That's the reason. It's make the algorithm converge fast.
Okay. So in other words, they use the faster convergence to offset the actual computing cost for the important sampling calculation, right?
Yes.
I saw that paper, the important sampling is kind of pretty computational intensive. It's
Yes.
big optimization there, yeah.
We should decide each weight for each sample, each iteration.
So compared with random sampling, the major benefit is we can achieve much faster convergence.
Yes, because we choose importance, right? And faster and better gradient, better sample phase with a grade.
Yeah. If you choose better gradient, that one I can understand. Although I still have the bias question left over there, but yeah, if you explain it this way, I can understand. Okay.
Yeah, but the bias issue should be still there.
Yeah, it's still there.
Yeah, you're right. But the question is that these papers they consider distributed machine learning instead of fast learning.
Right. Right. They're talking about.
They consider in the next they propose the resharding, right? They try to reshard try to hold
all the data are like evenly distributed,
and they do the shuffling to do that. I mean,
I see.
Okay.
Yeah, that makes sense.
Yeah. Okay. Yeah. Okay. Yeah. Why I need it in the future, you need to answer the question something in this way. Okay.
Okay.
You need to be prepared for this kind of question. I think that's very intuitive question everybody is going to ask.
Okay.
Okay. Yeah. Okay. Go ahead, please.
Okay. So, the second challenge here is that the data importance is imbalanced in every case. So a device, they may learn global trivial samples from it. So as in this example, for each device, they have a different importance distribution. So if our device, if the global samples and the importance is distributed differently, you may have inefficient learning involved here. So what they try to solve is to use the importance aware data sharding. So what it does is redistribute the samples among the workers, and also to reduce the amount to do the communication due to limited bandwidth. They must select the non-trivial samples to shuffle. So what it does in this figure, you can see that although in the beginning, each device, they have their own importance distribution, but after the resharding, they can achieve the same global importance. So in that way, the training won't be inefficient. And it
So here, I'm sorry, I'm confused. What do you mean by redistributed samples among workers? So there is a central server collect the sample and redistribute on the different devices in the collaborative way?
Yes, they will be those all will be aggregated and they will be redistributed. So yes, there will be an aggregation for this part, and they just need to redistribute all those samples.
Okay, that's how they avoid the bias here. Okay, yeah. Okay.
Okay, so that is the solution to the bias issue. And for a third one is what we try to do this, if we do the sequential implementation, it's going to be inefficient. So here's a graph of indicating how the process goes. So first, they do importance resharding, and then they do the importance computation. After the computation, they will do the gradient computation, and then they do the gradient aggregation. And all this process, if you do it in a sequential way, it's going to waste a lot of time here. So what they try to solve this is to do a bandwidth adapted computation communication scheduler. What it basically does is try to overlap the process here. So since the computation and the gradient computation and importance computation, what they try to do is the computation process, and the gradient aggregation and importance resharding, what they do is the network resource transition. So what they can do is they divide it into two threads, and one thread is our classic SGD. As you can see, it's only the gradient computation and the gradient aggregation and so on. The other thread, it tries to do the gradient aggregation, the importance computation, and the importance resharding. To give a better explanation. So
one question, sorry to interrupt.
Okay.
So the importance resharding will like exchange data between different worker nodes.
Yes,
right?
they will. Yes, yes.
So which will introduce extra like bandwidth consumption.
Yes. In theory, that should be an issue. However, they in this paper they didn't mention the in between transition. They pretty much just assume it is just neglected in that way.
Okay.
Yeah.
But for those 4 steps, you have a sequence, right? So you need to do something first, then do something later. Say gradient computation and gradient aggregation. They should be done after important resharding and importance computation, right? So
Okay.
yeah, how can you do this? This one looks like you do that simultaneously. How can you make them simultaneously?
Okay, so in this case, the importance which only the importance resharding that it needs to be done after the aggregation. So the other ones you can actually do this in a parallel way. So for example, you do the computation first, and then after you do the computation, you can already do the aggregation on this thread, right? But as soon as you do the gradient computation, you can send it to the other thread to do
the pipeline
computation. Yes. So you can do aggregation and importance computation in the same time to be exact. Yes, only the resharding and the importance resharding, you have to wait until the aggregation is finished, and then you continue on with it.
No, could you go to previous slide?
Okay.
No, yeah, this one.
Oh, this one. Okay.
Yes. My understanding is you do the resharding first, you do important computation afterwards. After that, you do gradient computation, right? So just you pick up the important data, then you do the gradient computation. And after gradient computation, you have new updates of gradients. You do gradient aggregation stuff. I mean, including gradient computation, definitely you can do compression, whatever. But there you should follow the sequence, right? So how can you do the resharding and the importance computation in parallel with the C and the A, the gradient computation and the gradient aggregation? I got confused by that part.
Okay, so what they show in this way is basically just when you divided it into 4 times, because at this point we only consider one thread. So all these threads, they have different tasks to do. But I don't think that means that guarantees that you have to do the something first to do the other later. So for example, the computation.
No, how about the gradient computation? If you don't do the important computation first, well, you didn't pick up the important data sample.
Excuse me,
how do you do? Oh, hold on, sorry, it's raining, so the dog is barking.
Oh, okay.
How can you do the gradient computation without knowing important sampled data? I mean, the importance of the sampled data. How can you do that? It's not a sequential thing. For this one, it's interleaved, right? Also, you do it simultaneously at the same time.
But okay, yeah. Yes. Yeah, and in this one, you can see that it is indeed you need to do the computation, but they're doing it in different threads, so it doesn't affect how it goes. See, after the gradient computation, right? After you finish this, you can either throw it to the aggregation part, so the system goes to aggregation.
I don't have doubt for that step.
Yes.
Yeah, I also understand. You know, within the computer you can have different threads. You can do the inter-thread scheduling. Yeah, yes. I don't have doubt about that too. I taught the micro P class before, so I know that. But the thing is, you need to follow a sequence, right? For example, WT. You need to do R1 first, then I, then C, then A. You don't follow the sequence? You interleave them? How? I thought that the gradient computation need to weight the importance of the data sampling as an input. Not like that?
No, actually, you don't really need to wait for it, because after you do the gradient computation, you can already try to see the importance. and then you can, and also you can do the aggregation. So I don't think you need to,
Why?
you need to do the.
So your gradient computation is for this round or for last round? It's for WT or is for WT minus 1? If it's all for WT, I think you need to wait for importance computation finish, so you can have some new fitting input. So you can do gradient computation. Afterwards, you can do gradient aggregation for WT. Unless, your I and R1 is not for WT round, it's for the WT minus 1 round.
This I, yes, this I is for the next time of this, because as you can see in this figure, you do the importance computation, and then you can send back to the thread 1, and what the computation is done is in the time of t+1. So it's in different timelines, as in this case.
But you do, even like that, right? You need to do that after global model come back so that you can evaluate how important your gradient is, right? So still you need to wait for CNA finish so that you can do R1 again. Say your current WT-CNA is for round 0, right? So you need to wait for the results, global model coming back so you can evaluate your gradient contribution so that you can do R1 and I. And then you go to the next round.
At the part we say about importance, at the first one they talk about the group-wise importance sampling. They don't need to always update for. You can use the already cached distribution. So you don't need to, as for in this part, you don't have to wait for to finish, because there's already a cached importance distribution in the device, right? So you don't need to wait for entire everything to finish the updating. You can wait for the update can be respond to the next time you do it, because we're doing the group-wise importance training. So I think in this paper you don't really need to do the importance. You don't need to do the importance computation after the entire resharding gradient aggregation is done. No, because every time the importance distribution is updated, they only updated a portion of it, right?
This is similar to the things Pauna presented the other day, right? But even for Pauna's paper, the paper Pauna presented the other day for communication and computation. Okay, move on, please.
Oh, okay. Okay, so so we're trying to say how they overlap I with the A. So how to overlap the importance computation with the gradient aggregation. So what they try to do is they adopt varying group sizes. So every time when they do this importance computation, they do this based on the time this gradient aggregation takes. Because in a true environment, the bandwidth or the transmission is going to change rapidly, right? So they need to adapt to the time gradient aggregation takes to adapt that.
Sorry. Again,
Yes.
I still have no question.
Okay.
For the paper Pauna presented the other day, they do the computation and the communication at the same time. Global updates is kind of laid back compared with the computation. But in that paper, they still do some correction. They store some local computing updates and they do some correction. You know what I'm talking about?
Yes.
Your global model coming back, you already finish a few more local iterations based on, old global model. Then there's new global model coming back. You do some correction for those each iteration's results. You store those results. But this one, it seems all your computation rely on, the cached information, the old information. You don't do any kind of correction, right? Although I think probably for the important computation, important resharding, it's not that important compared with federal model aggregation, global model updates. Is not that important compared to that one, but still, it's like you use old information to do the important computation and important resharding to make sure you're more I don't know, you see more delay or something.
Okay, so yeah, I think what they do is they do compute the old, but I don't think it's like the oldest, because they still update every time. It just takes time for them to catch up with updates. So I would say yes, in this graph they would compute in the importance based on the raw results, maybe a couple of rounds before, but every time they'll keep updating. It just takes time for them to catch up, because what they want to do, if they try to do this overlap, to completely overlap this thing, they cannot wait for the entire sequence to finish. So in that case, they do it this way, and they still keep the data. They still keep the importance distribution updating. They still do that.
Okay, Paula, what do you think? Are you there?
Yes, Dr. Pan, I'm here.
Yeah, what do you think compared to the other paper you present?
I think in this case, they don't have to have like that correction term or something. I think mainly because they do the resharding based on the aggregated gradients from the previous iteration, right?
Mm-hmm.
So it's like in the, for example, in the WT+1, we have the importance coming from the previous iteration anyways. So I think that's how they it gets adjusted that way, because I think everything is dependent on the R over here, the resharding part, more than.
Yeah. I got your point. What do you think is the R1 and the I actually is additional part, right? We use that, probably it's going to help. But if we don't use that, if we only keep thread one, it's just like the general file learning or distributed learning approach, right? Is something like that?
Yes,
okay.
Something like, yeah.
Yeah, R1 and R and I give us extra benefit. So we can interleave them. Even we use the older version of those things, it still help. Okay. Yes, Huai-an, please move on. Yeah, but I still feel confused about this part. How can we differ WT gradient aggregation from WT+1 gradient aggregation? They takes different time or something?
Oh, you mean why they take different time? This because the bandwidth is won't be always consistent in a true environment, so they might differ from time to time. They just try to make sure that the importance computation can always overlap the gradient aggregation.
It's like it's synchronized with gradient aggregation. Yes.
They make sure of that. So that's why they are varying the group size, because if they do too big, they're still going to need to wait, and that's going to waste time anyway. Yes.
Okay. But R1, R2, R3 is kind of fixed time, right? But for the I, you can adjust the group size to make
Yes.
it flexible.
Yes.
Okay. Okay.
Yes. Yes.
Okay. Yeah.
Okay. And to fully overlap R with C, this is pretty much a requirement. So restarting it just pauses when the aggregation begins here, and then it just resumes when it ends. So that's how they keep on track, and they just overlap the entire process. So that is pretty much how Mercury deals with these challenges while using the importance sampling to increase the efficiency to training. So here on the left side is just a unpolished. You just do the importance computation sampling with all the downsides we just mentioned there. And the right side is the Mercury, how they actually solve these problems. So here we have the system architecture. This is the entire process of how they do. So the first step here, they construct the mini bash from on-device data in the importance cache. So they get those mini bash and they throw into the importance sampler. So the next thing they do is the mini bash is fed to the model trainer and to compute the local gradient, which is located here. The third step, the gradients will be aggregated and the models will be updated. Then they recompute the data importance and update importance cache, which is right here. This is where they update the importance distribution of the data. And then they identify important data samples from the importance cache. And in order to do so, they can move it into the reshard executor to communicate with other devices and perform the importance aware data resharding. So what this is pretty much the demonstrations of how they do this and what we just mentioned back there. So that is the concept of Mercury. And now we will talk about the implementation setup. So applications and models, they have image classification based on ResNet, speech recognition based on BGG, and next language processing with LSTM. Now for the data sets, for image classification, they have CFAR 10, CFAR 100, SVHN, aerial image data set. Speech recognition, they have the TensorFlow speech command data set. For next language processing, they have the AG News corpus. For the devices, they use 12 NVIDIA Jetson TX1 and the Wi-Fi routers to connect all those devices. And the baselines, they compare with this. The first one is Tic-Tac, which is the one we mentioned with overlapping the communication and computation. And Adacom, which is the concept of local SGD without the sampling. So now
I think, yeah, I'm
yes.
sorry. I think it's different from Tic-Tac design, right? Because
Yes.
here, it's not like you overlap communication and computation. You still do, you know, the full stack or say full package of communication and computation. You do computation first, you do communication afterwards. You just overlap that procedure with the important sampling part, right? So why you want to compare this game with Tic-Tac?
Okay, so for this case, I think they try to do is because Tic-Tac is known for the overlapping situation. So they just
I think the only benefit they can do is, okay, if I do important sampling,
Yes.
I can achieve faster convergence. Even I follow computing plus communication, I can still do it better than you for communication and computing overlapping.
Okay. And
You know what I mean? So that's the reason why I think it's I know TikTok probably is most time efficient distributed learning, fast learning, whatever you call it, you know, designs right now.
yes.
But still, I think it's a little bit, you know, if you from overall time consumption point of view, yeah, I can accept that. But if you talk about overlapping, it's not like two overlapping scheme comparison. You know what I mean?
Yes, I know. I know what you mean. What I think I think what this paper tries to mention here is because TikTok it suffers from the problem. What I just mentioned back there is that when the bandwidth is limited, right? Because if the bandwidth is limited with these on-device distributed learning, the communication time is going to be very large. So in this paper,
But
they claim that
in your
Mercury
paper
they solve.
still, could you go to the over like the graph show the overall scheme?
Yeah.
You didn't address that issue for this paper. The bandwidth is limited. It still takes a long time for computing. No, not this one. The previous one. You have some the one I have most questions. The one page I have a lot of questions asking you. Yeah, that one. Yeah.
Yes.
Okay.
Yes.
This one. Yeah. For example, WT+2 channel condition is not good, right? It
Yes.
still take a long time for gradient aggregation. You didn't reduce any time.
Yes.
What I mean is, okay, this one you still follow computing first. Gradient computation is the computing, right? After that is communication. That's what this paper called a gradient aggregation, right?
Okay.
That's
yes.
what this paper do. Okay, if you forget about the R1, I, R2, I part, you forget about that. Okay, if we talk about general fast learning, for example, you still
Yes.
follow computation and the communication. You still follow this. But for the TikTok, they overlap computing with communication.
Yes. Oh, okay. Yes.
Yeah, this paper they don't.
Yes, they don't. They
Yeah,
just
the only benefit I can think of, okay, because you do the important sampling, you speed up the convergence. So overall, you can beat TikTok.
yes.
But you know, the benefit is now coming from, okay, you're adaptive to that bandwidth. No.
Yes. Yeah. Okay. I know. I
You know my part, right?
Yes.
So that's the reason why I said if you compare overlapping scheme, it's not fair comparison because this one is not overlapping scheme.
Okay.
Because the R1 things, RI things, I things, that's additional.
Yes.
Right? But
yes.
if you say, okay, I compare from overall time consumption point of view, yeah, I can definitely accept that.
Okay. Okay.
Yeah, that's my argument point, you know?
Okay.
Yeah.
Okay, so then I'll change the way to say it. So TikTok they can reduce the time only because if the bandwidth is high enough, right? If the bandwidth is too short, it doesn't benefit that much.
TikTok reduce the time because they overlap computation and the communication.
Yeah, yes. But so if the communication is already very large, so you still need to wait for
it doesn't matter. It doesn't matter. It's okay. You need to recheck the TikTok paper. The only thing is if communication time is too long, right?
Yes.
So you need to do more corrections because your local computing is already move on for another 5 or 10 iterations. You need to do the correction for all these 10 iterations.
Okay.
That's it. Yeah. It's nothing related to the bandwidth. The benefit they got in there is you overlap computation with communication,
Okay.
right? So yeah, I mean, I try to clarify. I'm not trying to criticize anything. I'm trying to clarify, you know, the contribution of these two paper. So when we do the comparison in the future for our own paper, we need to be crystal clear, you know, from which angle we need to do the comparison.
Yes. Okay, I understand.
Okay. All right.
Okay.
More on, please. Sorry.
All right. So we are at the. Okay, so we are at the results part. So in addition to performance, we just look at the speed up, and with the bandwidths, what 10, 50, 120, regardless of any, Mercury has a overall better performance than Tic Tac and Atacom in all those different data sets. And for sequential importation and scheduler, this is a comparison between the two. So in terms of test accuracy, BACC and sequential, they do similar if you only consider it the same iterations. But as an overall the time, because if you do a sequential, it's going to take a lot of time in one iteration. That makes the BACC scheduler much better in performance. So that's where they have their proof that the BACC is beneficial to the time efficiency. And the group importance.
Hey, Huai-an.
Okay.
Sorry for the interruption. I have one small question in this slide.
Yes.
Does it seem like the accuracy is the same for both of them? Like
Yes.
Okay. Because in both the figures, there's like slight difference. I know that the x-axis only changes, but the y-axis is the same, right?
Yes.
But it seems like there is some kind of change or in the accuracy value or not.
I would say like there is a slight, you slightly lose to sequential.
I think Paula, for this question, I think a sequential is better because they use most updated important sampling. Probably that's only the point differentiates this two scheme. The BACC basically use a little bit old cached information to do the important sampling. So that's the only thing I can think of.
Yes, that's I think so too. Yes.
Yeah. Okay. Otherwise, you are right. It should be 100% kind of overlap with each other.
Yeah. Okay. Thank you.
Okay. So, as for next part is the comparison between group importance and all inclusive. So the first one is group wise importance sampling, and the other one is all just you do the update all in once. So in terms of test accuracy, you can see that group wise is a bit slower than the all inclusive importance sampling, but in the time, in the overall time, you can see that group wise is much faster than all inclusive, because all inclusive it takes a lot of time in one iteration. You need to update all the data. Well, in group wise, you only need to update one at a time. And for importance aware and importance agnostic comparison, here's a graph showing that. So this is the importance aware resharding, and the red one is non-resharding. So as you can see, this is the point, and here is the importance agnostic. So these are like two extreme cases for it. And importance aware resharding is the middle point. So you can determine how much data, the amount of data you want to transfer. So with our conclusion is that Mercury, it enables efficient training by importance sampling.
Yeah, Huai-an, before you go to conclusion, did they
Okay.
compare with the TikTok?
In the overall speed
Oh,
of performance.
okay.
Yes, yes, yes.
Okay.
Yeah, the rest of them is just
sorry,
like with
could you
with
go, yeah. Go to previous one.
this one. Okay.
What do you mean by speed up here? Is it time or? What?
It means time, like the overall time to do so, because the training is like the iterations need to do and the computation and
So
communication time, right?
what's the baseline here? Baseline is just distribute machine learning without any kind of adaptive, you know, local SGD, without
Yes,
any local.
yes. That is
So
the
this
base.
one can speed up like 3.7 times.
Yes, as they claim, at least in the CFAR 10. Like if you put it in other applications, they might have slightly not so great speed up. Yes, but overall it's a big improvement in comparison to the former two.
But they play the trick of the bias, right? So
yes.
okay. Oh yeah.
Oh, okay. Okay, so the conclusion here is Mercury enables efficient training, and Mercury doesn't damage the accuracy too much. And Mercury addresses the challenges we just mentioned using first the group-wise importance sampling, the importance-aware resharding, and the BACC scheduler. And these are the conclusions for this paper. And any questions?